So last time we were talking about unique decipherability. Unique decipherability. And remember what that problem was is that you have a code which is really just a set of strings. For example, that might be 1. This is just an example. Each one of these things is called a code word. Okay, and then from code words you can make messages just by concatenating the code words and with repetition in any order you like. So there's no bound on the length of them. So for example, M equals ABBA, AB. There's a message. And the message is either uniquely decipherable, meaning that there's only one way to parse it in terms of the code words, or the message is not uniquely decipherable. Of course, this case is not uniquely decipherable because it could be it could be this code word followed by that code word, or it could be AB followed by BA followed by AB. So this message has two different parses. So this is not uniquely decipherable. A message that only has a single parse is uniquely decipherable, and that's abbreviated UD. And then the problem that we were looking at is given a code, is C uniquely decipherable? And that's a problem about an infinite set of messages. So of course you can't just enumerate and test each one. And at first it might seem like there is no algorithm for this. There shouldn't be an algorithm that's guaranteed to terminate in finite time. But in fact there is, and we were developing that algorithm last time. And the algorithm was, solution is you build a graph G with one node for each suffix of any code word in C. Okay, so that includes the trivial suffixes, which means the code words themselves. So let's just do this little example. AB, ABBA, BA, and then we would have suffix A, which is not in here, and suffix B. Okay, BA is already there. BBA is another suffix, and that's it, right? So these are the ones for the code words, and these are suffixes that are not code words. And then we had edges of two types. Okay, we had type 1 were the code words where C is equal to U. The edges from U to V, where U and V both represent suffixes, if you have a code word C equal to UV. Okay? So do we have any type 1 here? A code word which is equal to UV, and yeah, of course, from A to B, this is U, this is V, AB is a code word, and that's fine. And AB goes to BA because ABBA is a code word. So here's another one, and there could be more. And then we have type 2, where, again, it's an edge from U to V if you have U equals CV. Okay, so this is an edge from U to V if U is equal to CV. CV, well, U, this is a, U and V are suffixes, and of course they could be the trivial suffixes, and ABBA is equal to AB, which is a code word followed by BA. Okay, so this edge is both a type 1 and a type 2. The edges can be both types. Okay, now this little example is not particularly interesting because there are not a lot of interesting edges in there. But anyway, and I haven't even written in any other, there could be additional edges. This is just to remind you, we did this in great detail last time. And then the theorem that we were about to start proving, or we actually did start proving, we didn't get very far. The theorem is that a code is uniquely decipherable if and only if, now actually the way I phrased it last time was not uniquely decipherable, which I don't know why, that's sort of the traditional way of putting it, but is not uniquely decipherable if and only if there is a directed path in G of length, well, it's got to be greater than 0, at least one edge, from a node representing a code word to a node representing a code word. Okay, and here we see one. There's a path from AB, that's a node representing a code word, to BA representing a code word, and this example we know is this code is certainly not uniquely decipherable, and we see here an example that's consistent with the theorem. But we haven't really proven the theorem, and any questions about the statement of the theorem, or anything up to this point? Okay. Now this was all just by way of review. And then last time we started the proof at least in one direction. So that's what I'm going to do now, is do the complete proof in one direction, and then on your homework that's been posted on the class website, one of your problems, the third problem, is to do the proof in the reverse direction. But it's very similar, so it's mostly an exercise in really understanding the proof here, and then being able to reverse it. Okay, so we assume that the code is not uniquely decipherable. We can do that direction. So we want to be able to show that there is a directed path in G that satisfies this, this type. So assume G is not uniquely decipherable, so let M be a shortest message that is not uniquely decipherable. And of course, it's a message made from the code words in C, made from C. And it's the shortest of overall possible messages that are not uniquely decipherable. And from that, we're going to show that such a path exists. Okay, so what does it mean that it's not uniquely decipherable? It means that there are two distinct parses of this message M. So just pictorially, I'm going to let a line here represent a code word. And so this is one parse. And then there's some other parse where maybe it looks like that pictorially. This is just a cartoon. Okay. But of course, these two parses are the same length because they're both spelling out M. And what we started off with last time was looking at the two first code words in the two respective parses. And one I labeled C1 prime, and the other one was C1. So these are two code words. And what we argued last time was that the length of C1 prime cannot be equal to the length of C1. All right, so why is that? Because if the two had the same length, so if this was C1 prime and this was C1, here we are at the beginning of the message, C1 prime and C1, if they're both of the same length, then in fact they're equal because both of them are the beginnings of M. So they're two code words of the same length. You can have two code words generally of the same length in a code, but they have to be different. The strings have to be different. But here, they're both of the same length, and they're both equal to the beginning of the message M, so they must be equal. Okay, and I didn't make an explicit assumption, but the code has no duplicates. There are no duplicate strings in there. It's unnecessary to have a duplicate string. So if they were of the same length, they would have to be identical. Now, if they're identical, that means that if you look from this portion onward in the two parses, they both ultimately spell out the remainder of M, okay, which means that these two parses of whatever this message is, let's call it M tilde. Well, this is a message, by the way. What these two spell out is a concatenation of code words from the code, right? Because it starts here at the end of code words. So, or this code word C1 prime, which is equal to C1. So this is a message. It has two different parses, because if it didn't, then M itself wouldn't have two different parses. So M tilde, or whatever this is, has to have two different parses. So this would be a message that has two different parses, but it's shorter than M, and that contradicts our choice of the shortest message. Okay, so it's very useful to have the assumption that M was the shortest message. So we have the this conclusion that C1 prime is not equal, the length of C1 prime is not equal to the length of C1, and then we can just assume, without loss of generality, C1 prime, its length is strictly bigger than C1. Okay, so when we begin looking at the two parses, we see that the respective two first, yes, not first two, the two first code words, one has to be strictly larger than the other, and I'll just let that be the C1 prime. Okay. All right, so that being the case, we have two, one is strictly larger than the other. At the very beginning of this part, of these two parses, we have the longer parse and the shorter parse. That is, we have one parse that's proceeded further into M than the other one, strictly further than the other one. And we're going to keep that as an inductive assumption until we get to the very end of M. And we're never going to have a place where the two lengths of the two parses are equal until we reach the very end of M. Why is that, by the way? I said it was inductively, but in fact it's more direct than that. Why would we never have, as we add on more and more code words into these two parses, we're never going to get to a place where the two parses are the same length until the very end of M. Yeah?
It would contradict having the shortest message as uniquely decipherable.
Yeah, if we did have a place where they were equal, then we would have spelled out a shorter message. So it would have been spelled out. It would be a message that was writable from the code. So it's a message, and yet it would be unequal because, in fact, the two parses begin unequally. So if they had the same length at some point, that would be two parses of a message which was shorter than M. So the place where they become equal is at M. So we're going to be adding in more code words as we go through the different parses, and we're always going to have one parse be longer than the other. It's going to be the longer parse and the shorter parse, and that's going to hold until we get to the very end of M. And the amount that the longer extends beyond the shorter is going to be called the overlap. No, the overlap? Overlap is the wrong word. That doesn't suggest what it is. What's a better word for this? overhang. Okay, we could call it the overlap. It just wouldn't be suggestive of what it actually is. You can call it whatever you like. Okay, but anyway, overhang is a better word for what this is. It's the amount that extends past the shorter parse by the longer parse. Okay? So we will add. So we are extending the two parses to the very end. We will extend the parses by adding in one next code word, okay, at a time. And what we're going to always do is we're going to always add in the next code word of the shorter parse. Okay? Now when you add the next code word in to the shorter parse, I'll call it CC, that next code word, when you add it in, could make this now the longer parse. Or, depending on what its length is, it could remain the shorter parse. Okay? But what happens in either case, the overhang changes. Okay? If this is long, if what we add in, if CC is long, and makes this the new longer parse, then this is the new overhang. And if we add in something that's short, then this is the new overhang. It's just it's a suffix of the previous overhang, right? So this is the game plan. We're going to extend the parses by adding in one next code word at a time. Always add the new code word, and I'll call it CC, to the shorter parse. Okay, to the currently shorter parse. Okay, so let me remind you, there exists two parses. You may wonder, what are these code words that we're adding in? Where do they come from? They come from the existing parses. There are two parses of M. That's what we started with. M is not uniquely decipherable because C is not uniquely decipherable. So there are these two parses. And so we were just going to look at them one new code word at a time, sort of fleshing them out and moving left to right. And we're going to do it in this way. Always add the new code word to the currently shorter parse. And then when you do that, as I was saying, the new code word that you add in may extend the shorter parse past the currently longer parse, and then it becomes the longer parse, or it might not. Okay. And we're just going to do this until we get to the very end of M, and that's the way I want to consider the two parses. Now our goal is to prove that there exists a path in the graph G, which we've defined, from a node representing a code word to another node, or it could be the same one, representing a code word. So what I want to do is, as we're adding in these code words to the parses, as we're adding that in, I want to show that there's an additional edge that gets added into a path that starts at a code word, and that when we ultimately get to the end of M in this construction, we will have also found that path that we were talking about, the path that we're looking for. Okay? So let's just look at the very first step here, where you have the step is going to be the first step is going to be the following. Well, the way I have it written here, we're going to add in, this might be slight violation of what I just said. But You'll forgive me. Okay, we're going to start by adding in C1 prime. Okay? To two empty parses. Okay, so we start out with two parses that aren't going anywhere. They're just length 0, empty parses. And then you're supposed to always put in the shorter of the two next code words. But I guess this is a special case because the two parses are of the same length. And at any rate, I'm going to put in C1 prime first. Okay? So now I have one parse that has that length, the length of C1 prime. I have another parse that's length 0. So which of these two is the longer parse? This is the longer parse, this is the shorter parse. What's the overhang consist of? C1 prime. Okay. So the rule over here then says we should next extend the parses by adding in one next code word. Is that a question? Or no? Code word at a time. Always add in the new code word CC to the currently shorter parse. So the currently shorter parse is the empty parse, which means that we're going to add in C1. Yeah, C1 prime. We're going to add in C1, and the picture looks like that. Okay, so here's the overhang, the first overhang. All right, and this is a suffix of a code word, right? Because C1 prime is in fact a code word, so that's a suffix of a code word. That's V. All right. So I want to see from here that there is a path in the graph G that goes from a node representing a code word to a suffix of a code word. All right, under either type 1 or type 2 rules. So let's see if this works. If I consider the node that represents the code word C1 prime, okay, and maybe I want it to go to V, is there an edge in the graph that looks like that? No? Well, isn't it true that C1 prime is equal to C1 followed by V? Okay, this is a code word. This is a suffix of a code word. It's one of those degenerate or trivial code suffixes, which happens to be a code word itself. And this is a suffix of a code word. Okay? So this edge looks like a type 1. Okay? That goes from C1 prime to V. Now in my notes, what do I have? Yeah, type 1. You can also argue that there's a type 2 that goes here, or there's a type 2 from a node from a code word to V. Yeah?
I think only type 2 works, because here, if you write C1 prime as C1 multiplied by V, then the node would be from C1 to V, not from C1 prime to V. Because here type 1 is C equals UV, and the edge goes from U to V.
Yeah. Oh, okay. So, all right. So C equals UV. Yes, as a type 1, that should be C1 goes to V. Okay. But can we interpret this then as a type 2?
Yeah.
Okay, so we should interpret this as a type 2 because this looks like U equals C V. Okay, so type 2. Okay, so in my notes, I definitely want Did anybody print out the notes? Okay, so in my hand, I know that I'm holding notes that are not the current ones, because I fixed an error before I posted it on the website. So definitely I know that I want to talk about a path that starts at C1 prime, and my notes that I have say it's type 1, but we've just argued that it's type 2, and I hope that in what I put on the web has it as a type 2. Okay, so if anybody has that or has access to it, yeah.
Where am I looking?
On the top, well, sort of the first paragraph of page 3, where it argues that there's an edge from C1 prime to V. Is that justified as a type 1 or as a type 2 edge? Well, anyway, we've justified it here as a type 2. If you find the answer before the end of class, let me know.
Type 2 on this.
Type 2. Okay, good. So I'm the only one who has the wrong notes. You all have the right notes. But so why am I up here? Why don't you? Anyway. Okay, so in the notes I fixed it. I just didn't get myself a current copy. So from C1 prime, we have an edge to V, where V is the current overhang. Okay. So what we're going to show inductively is that as we add in each new code word to the parses, and we're going to add it in according to that rule, always adding in the next code word to the shorter of the two parses, we're going to see that we're going to be able to extend this path, the path that starts at C1 prime, and inductively that's going to be a directed path that's going to go to a node representing the current overhang. Current overhang is a suffix of it, will always be a suffix of a code word. So right now we have at the basis of the induction so basis, or you might call it an invariant statement. There is a directed path from the node for C1 prime to the current overhang and that is a suffix of a code word. So we're going to see that this holds inductively as we add one new code word after a while, at a time. And you can call that an inductive proof, or you can just say that this is an invariant property that holds as we go through this construction. All right. So let's look generically, sort of the inductive step. Generically, we've done this parse for a while. This is C1 prime. This is C1. And here we are. This is the overhang. And I'm going to add in the next new code word to the shorter of the two parses. Now, I've drawn the shorter of the two parses here to be the bottom one, which is the way we started with them over here. But the longer and shorter can flip-flop, all right, and you'll see that happening. So let's say we put in the next code word, CC, that's the next new code word, and it goes in the shorter of the two. And in fact, it extends beyond the longer parse, all right? So in that case, let me just, this new code word, CC, and the overhang, let's label that as V, okay? And let's label the overhang as U. Okay, now I know before I said that was V, but that was just at the very beginning there. Okay, now can you see, remember, inductively, we have a path, directed path from C1 prime, the node representing C1 prime, to the current overhang, or the node for the current overhang. So the current overhang here is U. And here's the new code word CC, and a new overhang V. All right? So does this make you think of one of the rules for going from U to V? What rule does this? Oh, did I erase the rules? That's bad. Well, let me just write them down over here. We have type 1, where C is equal to UV, and again, these are both suffixes of code words, and this is a code word. And we have type 2, where U is equal to CV, right? No. What is that second? Yeah, okay, fine. That's type, and U and V are are definitely suffixes of code words. Okay, so what do we see in this situation? Yeah. Right, we're seeing that CC is equal to U, V. U is the suffix of a code word. How do we know it's a suffix of a code word? Well, it's the overhang, so it's always a piece of the longer code word, of the longer parse. Or I could put it in the inductive hypothesis if I want. The inductive hypothesis is that we have this situation. There's a directed path from the node for C1 prime to the node for the current overhang, and that's a suffix of a code word. So we can say this is the inductive hypothesis as we proceed through this construction. So here we have CC equals UV, where U is the current overhang, and therefore it's a suffix of a code word. V is certainly the suffix of a code word because it's the suffix of CC. And so that's a type 1 edge in the graph, and therefore what do we have? We had inductively that there was a path, directed path from C1 prime to the current overhang, which is U. And now we have this additional edge in that path. So now there's a path from C1 prime to V. And what is V? V is the current overhang, and V is the suffix of a code word. So that proves the inductive step when the new code word extends the shorter parse to become the longer parse. Okay? Let's look at the other case. Actually, there are three cases. Let's say the new code word looks like that. Okay? It does not extend the shorter parse past the currently longer parse. Okay? So the currently longer parse remains the longer parse, but the overhang changes. All right, so U, just redraw this. This whole thing was called U. Okay? And now the current overhang is this little piece here, and that's labeled at V. Right? So here's the new code word that's being added to the shorter parse, and it creates a new overhang, which is called V. All right? And now, inductively, we had a path from the node for C1 prime to U, and now we want to see that that path can be extended to this V. All right? Under what kind of a rule? Type 1 or type 2? Okay? Now this is a type 2 because what we have is that U is equal to CC V. Okay? This CC is a code word, so U is equal to CV. And, of course, we still have to argue, in order to say that that's really an edge, we have to argue that U is a suffix of a code word. Why is U a suffix of a code word? I heard something. Yeah.
It was an overhang one step behind.
Well, this is the overhang. This was U was the overhang just before you put in the new code word, and inductively we're carrying along this inductive hypothesis that the overhang is in fact a suffix of a code word. So U is a suffix of a code word. Why is V the suffix of a code word? Yeah.
Because it's a suffix of a suffix, which is still a suffix.
Yeah, it's a suffix of the suffix of a code word, so it must be a suffix of a code word. All right? So U is a suffix of a code word, V is a suffix of a code word, CC is a code word, so U equals CV is a type 2 rule that demonstrates that there's an edge in the graph from U to V. And so again, we see that there's a directed path from the node for C1 prime to the node for the current overhang. V is the current overhang, which is a suffix of a code word. Okay? So, write down everything I just said, and you have the argument for the inductive step. And that's written down in the notes. Okay. What's the third case that I've omitted? So the one case was that the new code word that you're adding in makes the shorter parse the longer parse. The other case was that the new code word you're adding in is not long enough to do that, so that the previously longer parse remains the longer parse. And what's the other possibility? Yeah. Oh, yeah. You guys fit it out. Here, what is it?
But then it's the end that they're equal.
Yeah, they could be of equal length. Okay, so the new code word could make the two parses equal. Okay, so in that case, we want to argue that we want to see that the path that we've been building up is in fact runs to a node that represents a code word. Okay, so just before we put this in, just before we put this CC in, the path from C1 prime ran to a node that represented U, right? That was the current overhang. And now we're realizing that because there's a code word CC here, which fills, which makes the two parses equal, okay, CC is the same length as U. And CC is a code word. Now it's equal. Why is it equal to U? Why is the suffix necessarily equal to the code word CC? Yeah?
That's how we chose the U, is the suffix, or is the suffix as the length of that, is the overhang from what happened in the overhang?
Everything you said is true, but I don't think it supports the claim I want. U is definitely a suffix of a code word. It's the overhang, and now we've just said it's the same length as CC, and I just want to argue that in fact U is equal to CC as a string. Yeah, why?
They're both the ending of the message.
Right. Both parses are spelling out the same message M. So these coming at the very end of M, what they spell out has got to be identical. That means that this U was in fact equal to a code word. So the path that exists from C1 prime, which is a node that represents a code word, runs to a node representing a code word. In terms of this notation, which code word is it? So I'm claiming what I've just proven is that there does exist. I mean, inductively, we're holding this as we add in one new code word after a time, whatever the right thing to say is. As we add in one new code word at a time, one after another. This is an inductive property, an invariant property that's holding. ultimately, because we know that these two parses end at the same place, at the end of M, ultimately, you're putting in a code word here that fills the gap. It's just identically the same length as the current overhang. Okay? So at that moment you realize, and in fact we just argued that this code word, the overhang, is in fact equal to that code word. So we realize that in fact the path that we had up into that moment is a path from C1 prime, a node for a code word, to another node for a code word. And I'm just asking, just to see who's with me, what code word is that, does that path end in? In what? V? CC, yeah, CC. Just in terms of our notation, it's the CC code word. Okay, so okay, so just to end up, so ultimately we see that there is a directed path from C1 prime, or the node representing C1 prime, to a node for a code word, namely CC, which is the last code word added to the two parses. Added to the two parses in this construction. So that proves the theorem in one direction. That proves the theorem that when C is not uniquely decipherable, there is this path. Okay? Now, here's an exam type question that would be appropriate to ask. If the code is not uniquely decipherable, is it true? So we know, therefore, that this theorem holds, assuming we have already proven that. Is it true that the path from some starting code word to an ending code word always ends with a type 2 edge? Or is that edge, is that path, maybe I should make it a little bit weaker. Is it true that there always exists a path that ends with a type 2 edge? Anybody have an answer to that? Anybody have a question about that? Okay. Yeah. It's what?
Like one of the strings, one of the parses is longer than the other.
Yeah.
And that forms, as you attach the next code, it will form.
So you're saying yes or no?
Yeah.
Okay. So you're saying yes, and the argument is that, well, in this construction that we just looked at, it's showing a path, and in this construction, there was nothing special about the code that we assumed. This was just an arbitrary code that was not uniquely decipherable. That's the only thing we know about it. And in this construction that we said exists, we end up with a type 2 edge that ends. So certainly there has to be a path where from a code word to another code word that ends with a type 2 edge. Okay, this is a matter of looking closely at this argument and seeing this is perfectly general argument for any code that's not uniquely decipherable. So it always ends with a type 2 edge. Now you can think about whether there could be a path that even ends with a type 1 edge. That's the stronger of the two things that I asked. Is it always true that every path that shows that the code is not uniquely decipherable must end with a type 2 edge? Now, think about that one. You may see it on an exam. Okay. So we've proven this in one direction. Your homework asks you to prove it in the other direction. And really the proof is very similar. You just have to keep your wits about you and see what's happening in this construction and argue that if there is a path from a a node that represents a code word to another node that represents a code word, might be the same node, then you can construct a message that has two different parses. So what you'll want to do is, as you walk through that path, you'll want to build up two parses. And when that path ultimately reaches a node that represents a code word, those two parses will have the same length, and you'll therefore have your message that has two different parses. Okay? But you have to do this in generality to show that that's always possible. I guess there's one teeny little piece of this argument that we didn't, in the forward direction, didn't point out anyway. The path has got to be non-zero length. Okay? And it's non-zero length because back at the beginning, the C1 prime and C1 were of different lengths. Okay, so there's at least one edge. That defined the first edge of the path. If they had been of the same length, then we argued that in fact we had two code words that are identical, which we don't have. We assumed that that doesn't exist. So the path that we showed exists is in fact of non-zero length. Okay, let me just say a little bit more about unique decipherability, because I'm teaching you this for 3 or 4 reasons. One of them is it's an example of how you can think about problems that don't initially sound like graph problems or path problems, but in fact can be cast and looked at in a very convenient way in terms of path and path problems. And I hope this was understandable, and that when you do the reverse proof, that'll be understandable too. The literature on this started out with papers that did not use the graphical representation at all. They were just purely mathematical notation, and they were very long and involved, and people got confused, and there was a series of papers that got this proof wrong. It was kind of an embarrassment that the first attempts to prove this kind of theorem in the different language, in the more mathematical language, the not graphical view, they got themselves all bollocksed up in all the notation. So very convenient. I mean, I think this argument is really quite understandable. That once you view this as a graph and a path problem, it's certainly easy to see what's going on. But when you just did it with lots of notation, people got all confused and didn't get it right. So that's illustrating the utility of looking at things as graphs. Secondly, it's just kind of to me, always an amazing theorem that what looks initially like a problem may not have a finite time algorithm actually does. Oh, that's another thing I didn't do, but it's quite trivial. Maybe that should have been a homework question, is what is the complexity of the algorithm that actually builds the graph and then searches for a path? Okay, you should be able to convince yourself that even without any fancy data structures, you can build that in a time that's bounded by a polynomial function of the length of all of the input strings. To get the very best time that's known is quite tricky. There are some papers on that, but certainly to see that this is a basically efficient, not an exponential time process, you should be able to convince yourself of that. So that's sort of another amazing thing. The third reason is I just like it, and I'm trying to, and I've wasted a lot of time trying to prove that in fact there's an algorithm that determines whether the code is uniquely decipherable in linear time, linear in the length of all the code words. And I failed, and so has everybody else who's tried. So I'm trying to infect more people with that. And hopefully whoever listens to this class will be put on the web ultimately for whoever in the world wants to look at it. And hopefully somebody will be infected by that. And then let me just, if I have 30 seconds, show you another theorem about unique decipherability, because that's another reason this has very strange properties. Oh, and I should mention, on the class website there's a program that does implement this, basically this theorem as an algorithm, so you can run it and test any code to see if it's uniquely decipherable. So C, here's another theorem. C is uniquely decipherable only if summation 1 over d to the Li is less than or equal to 1. Okay, d is equal to the number of characters used in C. So in our codes that we've looked at, I've always just used A, B, so D is 2, but you can have as many different characters as you like. You can have codes of over 3 characters, 20 characters, whatever you like. And Li is the length of the of code word I. So it's necessary that this sum be less than or equal to 1, and therefore if you do take this sum and you find that it's bigger than 1, then you know that the code is not uniquely decipherable. And in the program that's on the website, it also builds in this test and another kind of more precise test than this, although I've commented that out. But you can look through the code and put it back if you want. And this is called I think this is called the Macmillan value or something. Okay. All right, thank you.